All right. So, as we looked at with Faraday's law, if you change the magnetic flux through a loop, there will be an induced current, and that induced current will attempt to oppose the flux change. And we can utilize this fact to make an electrical component known as an inductor that will work to resist current changes. So we define this ability of an object to resist a change in current and therefore resisting a magnetic flux change. We define this as inductance and denote it by a capital L and measure this in units of Henry. So inductance can always be thought of as electrical inertia, and inertia being a resistance to change. So we'll be connecting this to mechanics a lot. And the easiest way to make an inductor is just to wrap a bunch of coils of wire very close together, making this solenoid, because it has really strong confined magnetic fields, and thus would have a very rapid flux change if the current was altered through the loop. And the defining feature of these inductors is that inductors oppose changes in current, just like how mass opposes changes in velocity. If you apply a force on a mass that's moving, it's not just going to instantly stop. It takes time. And inductors can resist changes in current by utilizing this stored energy in the magnetic field of the coils. So this is a magnetic analog of capacitors, which store energy in an electric field. So we can really think of inductors as trying to regulate the current flow. So if the current is increasing, the inductor will act as a tiny battery to try and fight that increase. But if the current is decreasing, the inductor will act as a battery to try and restore the current back to what it was before. So inductors definitely do not have issues with currents. It's only changes that they'll oppose. And again, it's due to Lenz's law. If you're changing the flux, an EMF will be induced to create an opposite current. So if we were to give our inductors thoughts and feelings, they are happy as long as there's no current change. So here, if the current was increasing to the right, there would be a EMF induced to try and generate a current in the opposite direction to fight that change. And similarly, if we had a decreasing current to the right, the inductor would work as a battery to try and restore that current to its former magnitude. So we'll look at the direction of sort of the potential difference in each of the following cases, where we have a constant current to the left through an inductor, an increasing current to the left through an inductor, and a decreasing current over time. So first, in this first case, realize that inductors do not mind a current in them. So since there's no current changing in this first case, we're just going to simply have that delta V across this inductor is just going to be 0. So the potential difference is 0 in this first case for the reasons we exactly just talked about. Since the current is not changing, the inductor is happy, and therefore does not produce a back EMF. There's no flux change to fight. But then if there's an increasing current to the left, well, if there's an increasing current to the left, that means that there is going to be a flux change, so the inductor is going to prevent that increase. So therefore, it would try to send a current in the opposite direction as a response. So we could think of the inductor as acting like a battery with polarity oriented this way in order to fight that increasing current. And if we were to label the terminals of the inductor as positive and negative, we could label this end as positive and this end is negative, because again, it would attempt to send a current through the right through the inductor to try and reduce the increase. So again, the current is increasing, so it produces a back EMF to oppose that increasing current, because current would flow from negative to positive. It's important to note that the current actually doesn't flow that way. Like there's not a backwards current that's being generated. but it is a difference in potential that's attempting to weaken the change. And then we can imagine what the opposite would be if there's a decreasing current to the left. Well, if the current decreases to the left, then we just need the polarity to be switched to attempt to restore the current to what it was before. So if it's decreasing to the left, the inductor is going to try and send a current to the left to increase its magnitude. So that would look something like this. So since the current through the inductor is decreasing, the inductor produces a back EMF to support the decreasing current. So as a result, the right end is at lower potential. So now we can do this quantitatively. So since changing magnetic flux is caused by a current change, the EMF must be proportional to the rate at which current is changing. And we just define the inductance L as this proportionality constant, where we know the induced EMF has to depend on the current change, so we just give it that constant of proportionality L. And again, we can do that because we know magnetic field is proportional to current to the first power, as we saw with all of our Ampere's law and Biot-Savart law calculations. And notice this formula is actually very similar to the idea of a Newton's third law reaction force, where it's an F equals ma force opposite of the change. So first, for this example, we have the current through a 50 millihenry inductor is given by I of t is equal to 4t squared amps for 0 to 2 seconds. So first we want to calculate the magnitude of the back EMF in the inductor at t equals 1 second. So typically we're not looking at sign here, we're just interested in the magnitude. So our expression in absolute value says that the induced EMF across an inductor is equal to L times the magnitude of the rate of current change. So we're just going to take a derivative of the rate of current change. And there's nothing happening here with signs, so I'm just going to get rid of the absolute value on the derivative. So we're taking the derivative with respect to time of 4 times t squared. And then working that out, we get L times just 8t, doing the power rule. And then what we wanted is the EMF induced at t equals 1 second, so we just plug in. L was 50 millihenries, which is 0.05 henries, and then multiply by 8, and then t was 1 second, so we get 0.4 volts across the inductor at this time. All right, and then why is an EMF induced? Well, it's quite simple. An EMF is induced across an inductor if there is a current change. So notice that I of t is a function that's changing. So since there's a change in current, there's an EMF induced. So since the current through the inductor is changing, a back EMF is produced to oppose the change in current. So this would be directed in polarity opposite of the direction of current flow. All right, now we'll do a quick rank here. So we have all these different inductors. So some receive constant currents, some have increasing currents, some have decreasing currents in different time intervals. And we want to rank the magnitude of the average EMF induced in each of the inductors. So we can do this just by fundamentally realizing that the EMF in an inductor, the EMF produced by an inductor, I should say, is proportional to the rate at which the current through the inductor is changing. And we're just looking at magnitude here. So we're really just ranking each of these situations by magnitude. So first, constant current of 2 amps. Well, we'd get no EMF because the current is changing at 0 amps per second. Constant current of 4 amps, doesn't matter if it's greater current, still no EMF induced because there is no change in current. Then we got a current that grows linearly from 0 to 2 amps in 30 seconds, so we will have an EMF because we're increasing by 2 amps in 30 seconds, which is 1/15 of an amp per second. Then next, we're going from 0 to 4 amps in 60 seconds. So the current is increasing by 4 amps in 60 seconds, which is actually just the numerator doubled and the denominator doubled compared to the previous question. So that's also 1/15 amp per second. And then we have a linear decrease from 2 amps to 0 amps in 15 seconds. So this would be 2 amps of decrease in 15 seconds, which is 2/15 of an amp every second. And then lastly, it decreases from 4 amps to 0, so it decreases by 4 amps in 60 seconds, which would be 1/15 of an amp every second. So we're just ranking these rates of change now. So first, we can see that the lowest EMF induced will be a tie between case A and B, because there is 0 EMF induced in both of those cases. Then we have a three-way tie with 1/15 amp per second of change. So this would be C, D, and F. And then our 2/15 amp per second is our highest current rate of change, and that's E. So again, we're really just ranking the rate at which the current is changing through the inductor. So this is 0 amps per second. Then we have 1/15 of an amp per second. And then we had 2/15 of an amp per second. So the inductor is just going to oppose the change in current. So the higher rate of current change, doesn't matter what direction, but the higher the rate of current change, the more EMF is induced. So now we'll construct our analog of inductance as a sort of electrical mass. So inductance also kind of tells us how much energy can be stored for a given current. So we're going to complete this total analogy between inertia and inductance. So first we have the mechanics concept of inertia, and we're going to look at the formulation, or like the concept. So mechanics formulation of inertia, well, that's just the mass m, and its electrical analog is the inductance L. Then velocity, in mechanics, we just call that V. And then if we think of what the equivalent of electrical velocity would be, it makes sense to think that it would be current. Then for momentum, we define momentum as a product of inertia and velocity. So we say that momentum P is equal to mv. And similarly, we have this sort of electrical momentum which is the thing that objects resist a change in, and that's actually flux. So flux is our first new addition to the analogy, where flux, which can be written as L times I, is the electric equivalent of this momentum. Then for reaction force, meaning if you attempt to change an object's velocity, there will be a force in response, and we write that as the Newton's third law pair. F is equal to negative m dv dt, or ma. And then the reaction force, in terms of the electrical analogy, would just be the voltage, or the induced EMF. EMF is equal to negative L di dt. And then energy due to motion. Well, the energy that mass has just due to moving is given by the kinetic energy, which is equal to 1/2 mv squared. So the electrical analog will therefore just be the energy stored in the magnetic field, which is 1/2 times inertia times the velocity analog squared. So notice, just by constructing this analogy, we found a lot of equations that mirror each other. So the main new one is that the momentum equivalent would be flux. And by changing momentum, you get this sort of reaction force, or reactionary EMF. And this is also giving us the claim that we have this kinetic energy-like term for the energy stored in the magnetic field. So in this problem, we'll derive the expression for the energy stored in an inductor, so we'll more explicitly give that result. So using a mechanics argument, which we just did above, justify why it's reasonable to claim that the energy stored in an inductor is 1/2 times inertia times current squared. Well, we said this looks like kinetic energy. So if we were to complete our analogy, it makes sense that it should look like that. So if it truly is the electrical analog of mass, we'd expect the energy formula to take the same form as it does for kinetic from mechanics. But of course, that seems like a really weird argument, so let's just prove it. All right, so this circuit has reached steady state conditions. So we have a battery that's just pumping a constant current through the inductor. So the inductor is now happy. There's a steady state current. And as such, there is a bunch of magnetic field that exists inside the coils of this inductor. So again, there's some sort of a magnetic field inside the inductor right now. So thus it's storing energy. So just like when there's an electric field between capacitor plates, there's energy being stored. If there's a magnetic field, which is generated by current, then there must be energy in the inductor right now. So since there's a current through the inductor, a magnetic field is present. Pretend that I said present and not presence. As such, there's energy stored within this field. And then, is there a potential difference across the inductor? Well, the inductor only cares if there's change in current, and there's not. So since the current's in steady state, there's no current change. So di dt is equal to 0, and we said you need a change in current to get an EMF. But now suppose we instantly close the switch, which just effectively removes the battery at this time. So we have this circuit. So notice there is no source of current right now. It's initially I0, but the current will change. But just like a capacitor can do a quick release of current when the battery is removed, inductors can do that as well. So first, we're going to draw positive and negative signs indicating the relative value of electric potential, meaning if this was a battery, what would the polarity be? Well, notice that this I of t down here is going to decrease because we no longer have a battery supplying it. So the inductor is going to try its best to fight that change. So it's just going to behave exactly like a battery with positive and negative terminals like so. Because again, that would pump current out, or attempt to pump current out to fight the decrease. So due to the battery's removal, the current will begin to decrease. So this needs a downward current through an inductor that it's attempting to restore. So the bottom end has to be on lower potential. Or sorry, the top end of the inductor is at lower potential. Which is opposite of what the explanation says. This is top. No, I lied. Okay. Now we'll derive the energy formula explicitly. So we know that the power is equal to the current times the voltage, because we get coulombs per second times joules per coulomb, which is joules per second. But also, we know that I of t is something that varies, so we have a varying current. And also, we know that delta V across an inductor is negative L times di dt. And then multiplying both sides by dt, we get power times a small time change dt is equal to negative Li times a small change in current di. And now, as we usually do when we have differentials floating around, we integrate both sides. So if we integrate the power, we'd start from 0 energy dissipated, and we would end with some total energy dissipated U, because the total energy dissipated by the bulb has to be the total amount of energy that was stored inside the inductor's magnetic field. And then if we integrate both sides here, we initially have some current I0, but after the current is totally gone, there must be 0 current left. So simplifying, the left side just becomes the energy stored in the inductor. And then factoring out the negative L, we're just integrating from I0 to 0 of I times di, which would equal negative L times the integral from 0 to I0 of negative I di, just swapping the limits and adding a negative sign there. And we can see if you're just integrating x from 0 to x, well, you just get x squared over 2, and the negatives cancel, so we get 1/2 L I0 squared as desired. So again, just to summarize what we did, we said the rate at which energy is dissipated is equal to current times voltage, and we know the voltage across the inductor is negative L di dt, and then we just integrated both sides of the expression to get the total energy dissipated, which must have been the same as the total energy the inductor stored in the first place. And then we'll just do one example of calculating inductance, where you can calculate inductance, which is a geometric property, by finding the total flux through the object and divide by a current. And we do this just like capacitance doesn't depend on charge, inductance doesn't depend on current. So this is a purely geometric property. The only way to increase the inductance of a material is to alter its geometry. So first we'll verify that this formula works. So we had two different versions of induced EMF that we've looked at so far. So first, from Faraday's law, changing the color, we said that the induced EMF is equal to the number of coils times the rate at which the flux changes. And we'll put a negative sign there just to be consistent. But we also said that if it's an inductor, we define the induced EMF as a proportionality constant, L, times the rate that the current is changing. And since these both represent induced EMF, we must set them equal to each other. So we get negative N times the rate of flux change has to be equal to negative L times the rate of current change. And if we integrate both sides of this with respect to time, we would get the total flux, N times phi, is equal to L times I. And notice we also said this was our sort of flux relationship with momentum. So this kind of derives this fact that flux, the total flux, is equal to L times I. So we get N phi equals Li, so we just divide both sides by the current, and we get inductance can be computed by finding the total flux through a set of coils and dividing by the current, because flux will have this linear current dependence, which is going to allow us to ensure it's independent of current. I don't know what is happening with my drawing skills, but that's that. So for inductance, you got to find a B field expression so that you can find flux. And once you've found flux, you just divide by the current. So you just take the total flux and then divide by the current to get inductance. So the main example of this is just a solenoid. And it's just our standard solenoid, except there's some sort of material inside, probably an iron rod, that gives us a better mu value than mu naught. So again, if you wrap your fingers around the solenoid here, I point my fingers into the page for the top set of coils, and I wrap around and I get a leftward magnetic field inside the solenoid. And again, we assume it's constant. So we assume we get this nice constant magnetic field inside the solenoid. And we do know the formula for the magnetic field inside a solenoid, but just to always practice, we use Ampere's law here and remember the derivation for it. So the Ampere loop to draw, again, is a partially inside and outside rectangle. And we're going to label this side as X. And it better cancel because this side has no real meaning to us. And due to symmetry, many of the sides of this loop do not contribute anything to the magnetic field line integral. So the solenoid has N total coils, area A, and total length L. So first we'll start from Ampere's law. And Ampere's law states that the magnetic circulation, which is the integral of B dot dl, is equal to mu times the total current enclosed. I'm just avoiding writing the word core into the end because I have to keep rewriting it. So for our circulation, we have a B field that's circulating just for a distance x, because it's only the inside the solenoid horizontal segment that contributes to this line integral. And then for our enclosed current, we have a total of capital N currents distributed over a length little l. And then to find how many currents we actually enclosed, we multiply the coil density by x. So this tells us how many coils of wire we have enclosed in our loop. And then we put the current I in there. And again, I didn't actually state that we had a current I because it's not used to find the inductance later. So the magnetic field will certainly depend on the current, but the inductance will not, which is why I didn't include it as a listed quantity. So notice that as desired. This length x that we completely made up definitely cancels. So we get the magnetic field inside the solenoid is equal to mu of the core times the coil density, capital N divided by L, times the current we put through the solenoid I. So there's our expression. Notice this N divided by L is often written as lowercase n, giving us our mu times little ni formula. All right, total magnetic flux to the solenoid. Well, the total magnetic flux to the solenoid n phi is just going to be equal to the number of coils, capital N, times B times A. Because we have this constant magnetic field penetrating N total coils. So now just doing a quick substitution, we get N times the magnetic field due to a solenoid, which is mu core N divided by L times I. And then we're just given the area as A. You could definitely imagine a world where each coil is a circle of radius R, and this would be a pi r squared situation. And let's combine the ends now. So we get a mu core N squared IA divided by L. And then last step to find inductance is just divide by this current I, and notice that it is going to be completely independent of that current, which is what we claimed. So the current is just going to be total flux divided by the current supplied, and notice that this completely cancels out that one I in the numerator. So we get mu of the core times the number of turns squared times the area of each coil divided by the length. And this is our formula for the inductance of a solenoid, which luckily AP actually gives this to us. This isn't the most used formula out there, but you should be able to derive it from first principles. So again, we just found the total flux after getting the field, and then took out that factor of I. So it's kind of everything inductance related.